First one, of course, the conduction in Cartesian coordinate. Oh, okay. So I believe I have shown you basically how to do the energy balance for the Cartesian coordinate, but let's try and talk about it regardless. So first, the thing that we need to find to know is the, of course, Fourier's law. Mm, excuse my horrible handwriting. So you guys can see this, right? Is it clear for you, the writing and whatnot?
Yes, doctor.
All right.
Okay, dokter.
Okay. Uh, okay. So this is Fourier's law. If we are talking about in the x direction. Okay. But as we can see from this slide, so there is if you are only considering for x direction, which is this direction, only one direction. So before this, in the previous lectures, we have also considered only one direction. So in the x direction, we are not considering it is one dimensional. So we are not seeing it in 3D. So but of course, if it's in real life applications, everything is in 3D. So we do need to consider the heat transfer not just in one dimension but all three dimensions. So for real life applications, so that is what we are going to talk about now. So we have in the figure just now this uh, cube. So I believe this is XYZ. So wait. Okay, so in this case, okay, this is the x direction. So QX, and then this is QX plus DX, or delta X is the same. So the thickness is DX or delta X. And then we have, of course, it's in 3D, so we need to consider the other directions, which is this direction. I believe Y comes in on this side, right? Okay, correct. So QY, so in the Y axis, Y direction, so QY plus DY is the heat coming out in the Y direction. So I should change the colors. So finally in the so wait, um, okay, uh, so if you are in the so let's consider the Y direction will be QY, the heat coming in the Y direction, and then heat coming out in the Y direction is QY plus DY or delta Y. So in this case, uh, the DY, the thickness in the Y direction will be here. Okay, DY. I believe that's correct. Yeah, that's correct. Okay, so let's move on to the last direction, which is the Z direction. So Z coming in, well, it can come in from, okay, so in this case, it's coming in from the bottom. So Q the heat. Yeah. I don't know what's going on with my tablet. Wait.
Doctor,
Yes.
may I ask this QY DY, or should it be from the bottom to the top?
It can be either way. It depends on what you are. Wait, I'm not sure what's going on with my. It depends on your point of view. So if you're considering, that's why you need to, it really depends on whether the heat comes in on which side. So if it comes in from the bottom, then it will be QZ will be this is coming in, so it will be from the bottom. So this is it will come out on this side. Okay, but if the heat is coming up from the top, then it will be the other way around. So it really depends on where the heat is coming from. Is that clear?
Yes, doctor, thank you.
All right. So in this case, dz will be the height, of course, the height of the cube here, dz. Okay. This is dd. Okay, so if we okay, we have one thing is we have the Fourier's law. Okay. So we also need to remember that the and the what do you call that, the heat balance or the energy balance for whatever cases. Okay, so for any system, all the heat that is coming in equals to the heat equals to the heat that is coming out if there is no heat generation or heat accumulation. But so if it's in steady state, it will be, there will be no net heat generated or accumulated. Considering the total system, and it will be rate of heat in plus rate of heat generated so equals to rate of heat out plus rate of heat accumulation. So I believe we have talked about this in class or in one of the lecture notes, so you should know this. So we just need to divide all these things and one and try to calculate it one by one. So and then we can add it all together to get the energy balance equation. So in this case, for rate of heat in, so in this case it's pretty easy because it's the Fourier's law. It will be minus K A dt over dx. This is if we are talking in the x direction. Okay, so the area of this for the x direction will be dy times dz. Okay, why is this, why is this so? Because the if you see here, the x is coming in here and the x is coming out here. In the heat is coming out there in the x direction, so it goes through this area. So for that's why for in the x direction, the area will be minus k dy times dz dt dx. Okay. Okay. So okay. So for rate of heat up, this is we are talking about only in the x direction for now. So for the rate of heat out is actually the same. So dy over dx, dy dz dt dx, but for x plus dx, because this is going out, so it has already, the heat has already gone through dx, the thickness in the x direction. So what about the rate of heat generation is simply Q times the volume. So in this case, the volume of a cube will be dx, the height times width times length. If you remember, if you should know, this would be something that is very simple. So dx times dy times dz, you will get the volume. So what about the rate of heat accumulation? That will be rho. Rho is density. Cp will be the heat capacity because we're talking about heat. So dt dx. Again, we are talking about dt over dt temperature over dt times, which means we are talking about the change in temperature in terms of time. So the we as time flows, how we want to know how the temperature changes. Okay, so for this again, v volume will be dx dy dz times rho cp times dt over d temperature over dt. Okay, so since we already have all these, so we can just simply uh, plug it in into the heat balance equation that we have just now. So so the heat balance equation will be rate of heat in, which is minus k dy dz dt dx at x equals to x plus, because this is in the beginning at 0, so x is equals to x. So plus the rate of heat that is generated, which is q dx dy dz equals to the rate of heat out. So it is basically the same as the rate of heat in, but at x, at x plus dx, and then plus the rate of heat accumulated, which is volume dx dy dz times rho cp dt over d time. Okay, so we have this general heat balance. So if we divide everything, okay, so if we divide everything by dx, we will get divide by dx. Okay, so if we divide by dx, we will have minus k dt over dx at x divided by dx plus, wait, sorry, divide by dx, we divide by the volume, divide by dx dy dz. Okay, so in this case, because we have dy dz here, so this one cancels, but we don't, there is no dx here, so we still have divide by dx. And then for this, for the heat that is generated, so what we are going to be left with is only q equals to minus k dt dx at x plus dx divided by dx plus rho cp dt over d time. Okay, so okay, so we bring these two, together and rearrange the equation, so that, because what we are interested in is the temperature profile. So what temperature profile means is the change in temperature, right? So if you are talking about the change in temperature with time, so this is it. dt over d time. So let's isolate this. Let's isolate this so that we will get rho Cp dt over d time equals to q plus minus k dt over dx at x minus dt over dx at x plus dx. Okay. Divided by dx, of course. If you remember just now, we divided everything by dx. So if we let dx approach 0, we will get the second partial, partial, what do you call that? The second partial derivative of temperature with respect to x, or simply because if you remember in the slide, rather than this d, we have this d. So it just means that the substantial derivative versus the partial derivative. So in this case, we will be left with rho Cp dt over d time equals to q plus k. Then because this will change into, so this 1 over dx, okay, we simply bring it out over here. So if this times by 1 over dx, we will simply and then we take this as the change in temperature, right? Because this is dt over dx at coming out minus the temperature of the change in the temperature at the beginning. So we have dt over dx, right? So if we times this by 1 over dx, we will get d squared t over dx squared. Okay, so why has the negative sign disappear is because we are considering, we just flip this over to this side. So because we want we are always if you remember the cases before, we take the we bring the x2 to the front and then bring x1 to the back, so it becomes x minus x2 minus x1, so plus x1, sorry, because this is positive. So you times by this negative minus sign here and diminish this, so the negative sign here disappears. So the out becomes it becomes minus it becomes out, heat out minus heat in. So you will get this. Okay, so if we divide this, all of this, divide by rho Cp. This is annoying. Okay, so you will get dt over d temperature over dt equals to q divided by rho Cp plus k rho Cp d squared t dx squared. Okay, so the thermal diffusivity alpha, as I've already mentioned in the slides, is equals to k, the thermal conductivity, divided by rho Cp. So we can just change this into dt over d temperature over d time equals to q rho Cp plus alpha d squared t dx squared, because alpha is equals to rho divided by k divided by rho Cp just now. So but this is only in the x direction. So if you repeat this for all directions, y and z as well, it simply becomes dt over d time q rho cp plus alpha d squared t dx squared d squared t dy squared plus d squared t dz squared. So this is for all directions. So if you check back with the slides, so this is the same thing that we got. So d temperature divided by d time is actually the temperature profile. So if we have we know the time interval and we know one of the temperatures, and we have all these other values, we can calculate the temperature at a certain time. Okay, so is that clear for Cartesian coordinate? Or are there any questions?
Sir,
Okay, okay, good. So if there are
uh,
no questions, you have a
Sir,
question? Yes.
uh, is it possible if the Q, the heat,
Mm-hmm.
is different from each uh, its
Directions?
certain point, its direction? Yeah.
Yes, it is possible. So if, for example, we have the cube just now, right? If we have the cube just now, so but I'm hitting only I'm not hitting the top. I'm only hitting the here, the side here, and the bottom here. So that means the heat is coming in from the bottom, so QZ here, and the heat is coming from, this is the y direction, so QY. So there will be no value for QX. So it is possible. So and if the heat here is higher than the heat here, for example, I'm burning this with a bigger fire on this side rather than this side. So the heat coming from the y direction is actually less than the heat coming from the z direction. It is completely possible. So that is why we need to consider the temperature profile from when we are talking about temperature profile, we need to consider the heat coming from different directions because it can be different. Does that answer your question? So sorry, if the heat is different from different directions, so you will have dt dx, dt dy, and dt dz. It will be different it will be different because the higher the heat, the more the heat you provide, the change in temperature will be bigger. So if for example dz receives in the z direction, we receive more heat, so the dt, the change in temperature, will be bigger compared to the y direction, which if it receives less heat. So this dt dy and dt dz, d squared t divided by d squared dz squared will be different. So that is why we need to consider all directions. Does that answer your question, Andy?
So after yang dt over dx plus dt over dy plus dt over dz plus, and then Q2 we put what, doctor?
Oh, okay. So this
If the
Q
Q is
here,
different from each
yeah, that one
direction.
is, wait, I forgot the name of the queue. Uh, the name of the queue there. Let me see. Wait, I forgot. Okay. Is okay. So actually, for Q, if you notice, if you notice, I would before this QR. Sorry, Q X, Q Y, and Q Z. But in the final equation, we have Q with a dot here. Okay, so if you see here is Q with a dot. So Q with a dot is actually means Q. Okay, this Q is the volumetric
Hello?
heat rate.
Yeah?
So this is Qx, Qy, and Qz is the heat in only one direction.
Yeah.
But Q here is volumetric heat rate. That means it already considers the heat coming from all directions. So if it's given, so if you're supposed to calculate, if in the exam or whatever, you're supposed to calculate temperature, for example, they should have given you the volumetric heat rate, for meaning considering all directions at once. Does that answer your question, Andy?
Yeah, okay, doctor. Thank you, doctor.
All right. Okay, so if there are no questions, let's move on to something a little more complicated. Okay, so the second one you will see, the second system is the cylindrical system. Okay, so in this cylindrical system, okay, you can see that in R direction, and at Z direction, the height and the radius is pretty much in a straight line. However, this direction has a little bit of a curve, and that is what is gonna make it a slightly more complicated. So we if in the Cartesian coordinate just now, we see that in all the directions, the lines are pretty smooth, which is straight. So, but in this, excuse my horrible drawing skills. So, in this case, we consider, okay, I'm never gonna get this straight, so you just assume that it is straight. So, but here is a bit curved, because in the cylinder, just you can see in the cylinder, from inside to outside, it actually gets bigger. So if we cut the cross section like that, we will have a slightly curved line. So again, this is straight, and this is straight, and this is a little bit curved. Okay, and this is a little bit curved as well. Okay, and then this is straight. Okay, so let's give a name for all these directions. So we begin with the easiest one, which is the QR, the radius. So Q coming in is QR, and Q coming out is QR plus DR. Of course, you can choose to change R to whatever. If you prefer to use X, Y, Z, it's also fine, but I'm using R because if it's a cylinder, we are talking about radius, right? Okay, so in this case, the dr, the change in R direction will be here. Okay, then we consider another direction, because this is 3D. So what color should I choose? This one. Okay, and then we have direction. We'll talk about the straight lines first, so it's easier for you. So in this case, this is if heat is coming from the bottom, so QZ in this direction, and then of course it comes out as QZ plus DZ. This is pretty much the same as the Cartesian coordinate, of course. So in this case, we have the change in the Z direction to be here. Okay, the height. But if we are considering, where's my, okay. If you're considering the heat coming from the inside of the cylinder to the outside, from this direction, so because if it is if the heat is traveling from around the cylinder, it's not going to travel in a straight line, because the cylinder is curved, right? So we have this, I'll name this Q phi coming in, and then Q phi coming out, Q phi plus D phi. Okay, so what makes this a little bit complicated is that this is not simply D phi. This is actually R D phi. Okay, so why is this R D phi? Because we want to keep it dimensionally consistent. So we need to consider that this is in a curve direction. Okay, so derive the equation for this, but of course again we start with the we start with the general heat energy balance equation, which is rate of heat in plus rate of heat generation equals to rate of heat out plus rate of heat accumulation. So we divide this into sections, and then we try to solve it one by one, and then we combine it back together so that it's easier for us to understand the derivation. So let's start with the easy ones first. So which is the rate of heat generated. So rate of heat generated, if you remember just now, is equals to volumetric rate, rate of heat times the volume. So in the Cartesian coordinate case, it's pretty easy because it's dx plus dy plus dx times dy times dz. Okay, but in this case, we can consider, okay, first dr here. So we have dr times times dz here, dz, and then times r d phi. Okay, because in this case, the thickness in this direction is given by r d phi. So so we have this, and then we let's talk about the rate of heat accumulated. Okay, so rate of heat accumulated, if you remember, is similar to the Cartesian coordinate, in that is V rho Cp dt over d times. Okay, but in this case, again, the volume is different from the Cartesian coordinate, in that it's dr dz, is it dz r d phi rho Cp dt over d time. Okay, so we have this these two of all, if you remember the what do you call that, the heat the energy balance equation, we already have two of the factors, the heat generation and the heat accumulation. So we are still left with the rate of heat in and also the rate of heat out. So let's try and solve that now. Okay, so for rate of heat in, I hope you can understand you guys can understand my handwriting. Are you having problems with my handwriting? Is it really bad? Anyone have any problems with
No,
my?
doctor. It's
Okay,
good.
ah?
It's good.
Okay. That's good. I'm so glad, because if I type if I type everything, you can see better, but it will probably take until tomorrow until we finish. Okay, so it's easier for me to write. Okay, so in this case, rate of heat in is equals to Q R plus QZ plus Q phi. Okay, simple. It's pretty simple. Because of course the rate of heat in is equals to rate of heat coming in from all directions. So it's the same as rate of heat out. Rate of heat out is the rate of heat going out in all directions, which is QR plus dr plus QZ plus DZ plus Q phi plus D phi. So still pretty simple, right? I hope you can follow. So the problem is we need to this usually like in the Cartesian coordinate, we can take this out minus in. Okay, so in this case, is we need to simplify things a bit. But before we simplify things, we need to make it a little bit more complicated. In that, okay, so we want to change this into something that can eliminate QR. So we use the Taylor series expansion, which is just a way to expand the equation. So we have QR plus DR, which is this one. Oh wait, I need to charge my laptop. Okay, so is equals to QR plus dqr, the change in heat in r direction with because in that over dr times dr. Okay, so is because how you explain this is if you eliminate this, because dr can be eliminated by dr, right? So if you where's my okay so if we are left with qr plus dqr, so it's actually the rate of heat in plus the change of heat. So we can repeat this for the other two directions. Qz plus dz equals to qz plus, this is the same thing, dqz over dz times dz. Okay, so same with the phi direction, plus d phi is q phi plus dq phi d phi times d phi. Okay. Okay. So in this case, we already have, if you can follow, we already have the rate of heat in, rate of heat out, and rate of heat generation, and rate of heat accumulation. So we can simply substitute everything into the general energy balance equation. So for the energy balance will be rate of heat in all directions. So QR plus QZ plus Q phi. Q phi. The mouse says one thing, but the hand writes something else. Okay, plus the rate of heat generation, which is Q times the volumetric heat rate Q times the volume. So dr dz, and then r d r d phi. Okay, this is the volume, equals to QR plus DR plus QZ plus DZ plus Q phi plus D phi times the rate of heat accumulation, which is the volume times rho Cp d temperature over d time. So we have dr dz r d phi, so rho Cp dt over dt. Okay, so if you remember the expansion that we did just now for q r dr, qz dz, q phi d phi, so we can substitute this into the equation. So we will get for this side, the right hand side of the equation will be qr plus dqr dr times dr plus qz plus q dqz dz dz plus dq phi divided by d phi. Wait, I missed something. Qz for q phi first plus dq phi over d phi plus this one lah, plus plus dr dz r dz r d phi rho Cp dt over d time. Okay. I hope we can follow for now, so far. So, for you can see for the left hand side of the equation and the right hand side of the equation, we can simply cross this out. Okay. So we can cross this out and we can cross this out. Okay. So, and then if we bring over, because if you remember, in this case we want the temperature profile. So the temperature profile is this. So we want to isolate this, meaning we want to bring this here. So we want to isolate this. So what we do is we bring the remaining stuff onto the other side of the equation. So if you do that, you will get Q times the volume just now, dr, dz, r, d phi, minus, because we are bringing it to the other side, so everything becomes minus. So dqr dr dr minus dqz dz dz minus dq phi d phi d phi. Okay, and then equals to the volume dr dz dr d dt over temperature. Okay, so we have, if you can see here, we have actually isolated this temperature profile. Okay, so let me see. Okay, so if we remember Fourier's law, we have QR equals to minus k dt dr times the area, correct? Or minus k area times dt over dr. So in this case, we substitute the area, because the area in the r direction, is much like the Cartesian coordinate, is this. Okay, so area is equals to this equals to dt over dr. The area is dz times r d phi. Or if you want to remember it easier, is actually just everything that does not include the direction in the r direction. So dz is the height, and then r d phi is actually the other line over there. Okay, so we do the same. We do the same thing for the other two directions. So minus k dt. Remember, this is dz. So for the area will be k dt dz. So for this one is dr. Okay, r d phi. So there's no z here. Dz is not here. So dz is actually here. Okay, so it's the same thing for. So it's the same thing for the phi direction, but please remember that for phi is slightly different, because it's minus k dt. It's not over d phi, but it's over r d phi, and the area is dr dz. So why is this not d phi but r d phi? So in this case, this is r d phi because we are considering the change in temperature with the change in the direction. Okay, so the change in the thickness lah, for the change in thickness. And in this case, the thickness, even though the other two, the thickness is dr or dz, in this case, the thickness is r d phi. So that's why here it has to be r d phi and not simply d phi. Okay, so if we have all this Q and we substitute this into the energy balance equation just now, okay, if you have any problems, please feel free to interrupt me, okay? I heard someone switch on their mic just now. Okay, so just now we have the equation to be Q dr dz r d phi. Okay, just now was minus dqr dr and minus dqz dz minus dq phi d phi d phi equals to the volume rho cp dt over d temperature. Okay, volume is of course you know already, dr times dz times r d phi. Okay, so all this for all this q, q phi, qr and qz, we substitute this into the equation. Okay, so what we will get is q dr dz r d phi. So if we plus, it becomes plus. Why it becomes plus is because here there is negative here. So if we minus and minus sign and minus sign, we will get positive sign. So in this case, d over dr, because we are only substituting this. So for this is still there. Can you see? This is still outside. So we bring this outside. So we have q, sorry, not q, k dt over dr, because we have, why we have dr is because of dr here, we bring it here. Okay. So times the area just now, dz r d phi. So in a similar manner, we substitute qz and q phi. So if for qz we have d over dz, and then we substitute qz here, so we will have k. So the minus sign has disappeared because it became a plus sign here. Okay, minus is positive. K dt over dz dr dz, yeah, wait, dr at the area just now was dr r d phi, right? But and then r d phi, no more space here. Okay, so dz here is from this. Okay, so plus, so this one we need to pay a bit more attention to q phi because it's not the same as the other two directions. So we will have dq phi. Okay, dq phi k over r dt d phi. So how do we get this? Okay, if we see just now, for q phi, we have this kr here. Okay, so this is how we get the kr here. And then for dt d phi is here. Okay, and then we consider the area dr dz. Okay, and then here if you see in the balance equation, we still have d phi here. So it's d phi. Okay, so you can see for the other two directions, we have r d phi. But this one is simply d phi because yeah, because it's only d phi here. Okay, equals to here lah, the temperature the temperature profile here. So if we write in full, we will have dr dz r d phi dt, the temperature, over dt. Okay, so we will have this expanded equation. So so to get the equation that you have seen in the slide previously, we divide everything. Okay, so we divide everything by okay, so we divide everything by the volume, which is dr dz r d phi and the thermal conductivity. Okay, so divide the equation. So what we will get is okay, if we divide everything, we will have 1 over r. We bring the r out just now. D over dr r dt dr. Okay, so previously we have r inside. If you remember, we have we have kr for the r direction. So we leave the r inside. So when we divide this, we will get we can cancel this and this, but there is no r for the r direction. So we will have 1 over r. So plus 1 over r squared d squared t over d phi squared. Okay, so if you try it out later, you will remember that for the phi direction, we already have we have k over r. So when we divide by k is cancelled out, but 1 over r becomes when we divide again by r, we get 1 over r squared. Okay, plus d squared t dz. This is the easiest because we have k. For the z direction, we have k, and we also have dr dz r d phi. So everything cancels out beautifully. So we also have q. Just now we have the volume, the q times volume, right? So the volume cancels out, but we have divided by k. So equals to rho cp over k dt over dr. And then if you remember, the thermal diffusivity alpha is equals to k divided by rho cp. So this is actually equals to 1 over a dt over, oh sorry, not dr, dt over dt. dt over dt. Okay, so this is the equation for cylindrical coordinates. So you can see the equation here. Okay, actually, okay, actually it's already 11, but I would like to continue and finish the spherical coordinate. Since I believe that the previous lecture was quite short, less than 2 hours, are you guys okay if we continue and finish the spherical coordinates? Or do you want me to continue next time? Or you want to solve it yourself at home? Well, you are at home. I mean, solve it later. What do you...
Sorry, doctor. Actually, we have another class that
Okay.
already
All right then. So we'll finish
started.
here. Okay. So you, if you want, you can. Okay. So sorry. Yeah. That means I'm keeping you. So you can try it out later. But if you prefer to discuss the spherical coordinates in the next class, please put it in the WhatsApp so we can continue to discuss this in the next class. Okay. So I'll not keep you guys. Thank you for listening. I hope everything was understandable. And as usual, if you don't understand, you can message me. Okay. Thank you guys. Have a good day. Enjoy your next class. Don't forget to sign in. Okay. Don't forget to slide in your attendance.
Yeah. Thank you, doctor.
Okay. You're welcome.